we can get started. Okay, so how's everybody doing? It should be, you should have gotten, okay, yes, everyone should have gotten the feedback from the homework back. I hope that has been seen. There is one thing I need to quickly announce. Okay, yes. So two things. The TAs have asked me to make a special note that submissions to the homework ought to be done in PDF. Okay? So when you are advised not to just simply take a picture and send it off. Try to do it in a PDF, which really helps us, and especially the TAs, mark your work so that they can annotate and they could also open it more easily. Okay, because PDF is something that can be opened on many devices without problems. Whereas if you use picture format, sometimes that goes wrong. So please do open it up and do your submissions in PDF. Okay. The other thing that I should announce is that, as I was saying before, the homework for problem set 1 has been marked, and you should all have received some feedback on it, if there's any feedback to be given. And the thing that we want to do, and that's something that we will record some videos that should go along with the exercise classes, are so-called common mistakes in the homework. So it's really just things that the TAs have noticed that weren't done, or that people commonly make similar mistakes. And then I've asked them to either record them in a video or at least write a short note that we will post on the course webpage, just so that you're reminded, or you are being pointed out, saying that, okay, these were some of the common mistakes in the exercise classes. In the homework sets. Okay. That's another thing that is coming up. Okay. Any questions or comments about these announcements? I don't see anything from the floor. So in that case, let's just get started with the lecture. We have quite a bit to cover today. But as usual, let's start with a quick recap from last time. And in particular, I wanna discuss what we talked about last time, which was the so-called uniqueness theorem. Okay. And of course, last time around, I gave a very technical account of the uniqueness theorem, which specifies all the conditions in which you are. Okay, I'll come to that in a moment. You are able to find a unique solution to the Poisson equation. Okay. Okay. There was a question from Harry. Let me get to that first. So the question is whether there's any information about the midterm. Do you mean in terms of when it's going to be held, or any other information? When and content. Okay. Very simple. We are now supposedly in week 5. Let me double check. 1, 2, 3, 4, 5. Yes. So this is week 5, and you can expect the midterm to be in week. That's right. That's right. You can expect the midterm to be in week 8. But that should be this. That is 5, 6, 7. So it should be in the last week of October. Okay. And in terms of the content, it is everything that will be covered until week 7. Okay. And so, that should be pretty much everything from the static electromagnetic fields and then all the way to all the methods that we're going to discuss about how to solve the Poisson equation. For example, something that you will do in this exercise class, sorry, homework set, which is methods of images, that's going to be included. What we're going to do today, which is multipole expansion, is going to be included. And then what we're going to do next week, and for maybe half of the week after that, so half of the week 7, is so-called the separation of variables. That is going to be included. Okay, so basically, very simple. It's going to be static electromagnetic fields and methods of solving the Poisson equation. Those are the 2 things. Okay, does that answer your question, Harry? Okay, good. I will make a more formal announcements about the midterm probably next week, most likely next week. Okay, anyway, thank you for your question, Harry. Okay, returning to the lecture, the uniqueness theorem. Okay, I'm not going to give you the big, long mathematical definition, but one thing that is important to know about the uniqueness theorem is that if you can find the solution, and it's of course to the Poisson equation plus the boundary conditions, then you're guaranteed that those are unique solutions. And that is the power. Right? Because if you can, exchange maybe a very difficult looking problem with something that is much more simple in which you know how to solve, then you are guaranteed that is the solution. So the example that we showed last time is so-called is a conducting plane. Okay? A conducting plane in which it is kept at some constant potential. Here we set it to 0, and then there's some charge Q put at some distance d of this conducting plane. And of course, this is a situation where what we showed last time around is that it's going to be difficult because in this conducting plane, what really is going to happen physically is that there's going to be some charge. Just put this in green. There's going to be some charge distribution spread around the surface. Okay? Now, that by itself is, creates for a little bit more complex situation. But I am perfectly able to exchange this scenario with something that looks like this. If this is Q again, and instead of having a conducting plane, I simply have, I can put a scenario where I put a negative charge here in such a way that, again, this is also phi equals to 0. And so by virtue of the uniqueness theorem, I know that if I find a solution to this one, to the green one on the right, then the solution must also apply to the blue one, because they solve the Poisson equation and they satisfy the boundary condition. Now, there is a caveat, and this actually came about through a question that was asked last time, and that is, well, what if you actually had some very thin conducting layer and you have charges on both sides? The thing is, though, this scenario here in green is only half the story, right? In a way, I know for the blue scenario that all of here in the bulk, I know that the phi is constant. But I'm interested in the region here, right? Z bigger than 0. And so I can use the green, the solution to the green, but only at Z is bigger than 0. Okay? Now, in other words, and this is more or less kind of like a rule of thumb, is that, you know, when you have this conducting plane, I can put a virtual image like this minus q, but only in the region that is where you're not looking for the solution. Okay? So if you're interested in this area here, then, you know, there's typically not an image. It cannot exist an image, virtual image, that goes in there. And that is a caveat that you'll have to bear in mind. Now, today we're going to release the next problem set, and it's simply 2 exercises where, you know, you're going to learn to look for solutions of this using this method of images. So that's just something to keep in mind when you do so. Okay, so that's the recap from last week. Let me quickly open up the floor to see if there are any questions about this. No questions? Good. Right after the lecture, we will release the problem set, and so and then there will be a recorded exercise class, or to also help you, like, as a guided way to do these solutions. Okay, now let's go to the main part of today's lecture, and in today's lecture, we're gonna take a slightly different approach to solving Poisson equation. So, as we've all seen the Poisson equation now, can anyone give me the Poisson equation? Anyone? This is arguably the most important equation. Laplacian of phi equals a constant. Very good. Okay. Well, okay. That's it doesn't have to be a constant, right? Laplacian of phi equals to the source in this case. And so, indeed, so if we just look at the Poisson equation, then we have phi equals, and I hope I get the minus sign right. I think there is a minus sign. Rho over epsilon naught. And epsilon naught? Always forget the constants. Yes. Yes, there should be an epsilon. Yeah. Pretty sure. Okay. So this is the Poisson equation in electromagnetism, and we have the corresponding one, the 3 Poisson equations for the vector potential. Okay, so indeed, the potentials are governed by Poisson equations. Okay, governed by Poisson equations. Okay. And so we've actually seen, and this is something that I've merely you know merely put it there like this, but the solutions are of the following form. Okay, we have the integral of rho the charge density, and then we have r minus r prime d prime. Okay, so we're simply, what we're going to do is we're going to integrate the rho over over some volume, and in this case again remember that the prime is the coordinate system for inside my source, and r is where I'm interested in. Okay, whereas then I just to highlight this, if this is the origin, then this is r prime, and here this is r no prime, and so what we're interested in is this arrow over here, which is r minus r prime. Okay, now similarly, again, there may be some epsilons and minus signs that I'm forgetting. Similarly, A is given by J over R minus R prime. And so that's something that we, that would be one very easy way to get phi, to get the field, right? Is simply do this integral. And the question, of course, is it usually an integral that you can do? The answer is typically no. For anything generic, for rho and for j, it's not something that you can do by hand. And so it's something that we need to somehow find ways in which we can still try to solve this. And that's where the concept of multipole expansion comes in. So let's take a look at the so-called multipole expansion. The first thing you can ask yourself is what happens if I have some large distribution. Okay, this is rho as a function of r. This. Okay, and I can ask the question. Okay, well, what's the field given this point over here? Now, for anything generic, it could be a very, very complex expression. Exactly where phi is, or what phi is, and how E represents itself. But what if now, instead of this R, I'm going to make R, I'm going to go very far away. So this is R dot 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 dot, and all the way up to here. Okay. So if R is much, much bigger than R prime, so that where I'm considering R is much bigger than the size of the object itself, well, then I can actually have something that looks, I can approximate this to something. Can anyone think how I can approximate the potential if I'm going very, very far away? So Alex writes KEQ over R. Okay, indeed, KEQ over R. Okay, now what is this potential corresponding to, Alex? So why would you suggest KEQ of R? As if it's a single charge. Okay, good. If I go very far away, I can't see the size of this object anymore. And I can write Q is just the integral of rho in throughout this whole thing. And I just get the total charge of this distribution over here. That's good. And now Ling is writing that this is so-called monopole, and this is exactly where I want to go towards. Right? So this would be a monopole. And I'll explain this concept of poles in it. So indeed, if I go R is much bigger than R prime, then I can just approximate this to approximate as a point charge Q as the total charge. Okay, so that's good. Now, one obvious question here is the question, well, okay, what if the total charge equals to 0? Okay, we'll give people a minute or two to think about this. But what if the total charge distribution? It's not that there's no charge, right? It's just that the plus and the minus charges are, somehow distributed in a way that, the total charge equals to 0. The question is then, what happens then? Okay, let's take a look at some of the answers that people have provided. So Dominic says phi is close to 0. Anson is going a small step further, says is a constant. So the first two answers are I mean, yes. If you go very, very far, there's no charge, right? If you go to infinity, there's no field, there's nothing, and that's fine. Okay, so yes, 0 and constant are in principle correct if you go to infinity. Okay, now, of course that's not well. I mean, that would be the very trivial answer. but we'd still like to see if there's maybe a tiny little contribution. So Ching Pang says dipole. Okay. We'll again have to define what dipole is, but and that's actually what Jason is saying. Depends on how the charge is distributed. Right, so left is a negative sign, negative charge, and on the right there's a positive charge. Then it's a dipole. Okay, and so yes, that is kind of how you would write a dipole, and we'll get to that. And then yet one is saying split in half. I think what he means again is something very similar to a dipole. Well, okay. The answer is, of course, you don't necessarily know what actually goes on, but that is important is, of course, that if q equals 0, you don't just have a point charge or phi, but you can still get something else. And so let's consider indeed what Jason and what others are suggesting. Let's take a look at a physical dipole. Okay. This would be the easiest way in which I could create something where the total charge is 0. Let's draw this physical situation out. Green, and let's put a charge here. Okay. Let's call this plus Q, and let's put a charge here, minus Q. And let's consider, ourselves to be in, to be somewhere here. Okay. This is the observer. And so let's just draw some lines. Okay. This is a little bit awkward. Draw this in a so I can this, and there's one here. Well, okay, that doesn't matter. And then there's something here in the middle that I can draw here as well. Okay, now let's put in all the different things. So we've got a plus Q and we've got a minus Q, and let's make this total distance here. Let's call this D. Okay. And so if I stand right in the middle, then indeed, wherever I look, I expect, the total charge to be 0. And so from here, let's say that's the origin, that's the observer. We call this R. And, let's label the other one. This is R plus, and this is R minus, okay? Because it's plus sign and negative sign. And if you will, I can make this theta, give it some angle. Okay, so this would be, arguably the simplest thing I can do, right? So that if I look far away, then the total charge is 0, right? There's a plus charge and a negative charge. So if I, in this case, make R, the distance of R much bigger than D, then the Q equals to 0. Okay. Okay. Now, if I had to write down the potential of this system as a function of R, the question is, of course, this is a dipole. Consider a dipole. And now I'm asking phi as a function of R. Who can tell me what the potential is for the system anywhere as a function of R? But Dominic is saying 1 over r cubed. So we're not going to go into the approximation of very far away yet. I'm simply asking, what is the field? Okay, what is the scalar field in this case, in this situation that I'm plotting? I'll give people a minute or two. So Alex is saying KE times Q over R minus, and then plus, sorry, QR plus minus QR minus. Okay. Anyone agree? Disagree? Okay. Now this situation is exactly the same as we had before when we looked at, for example, the recap. Okay. So when I have a charge and a conducting plane, I can just put an image charge here, and indeed I get Q and minus Q. And so I end up just with the potentials due to superposition of the two individual point charges. Again, here, Alex is right in saying that the potential is simply KE Q R plus. Okay. And make the notation as crisp as possible, like this. Basically, the distance from the positive Q, which is R plus, and then the distance from the negative Q, which is R minus. And now let's say that we're interested going far away. Okay. Now let's see if we can turn this, and this is exactly what Alex is saying. Can we express things in terms of R? Not R plus, not R minus. It's just so that we pick an origin, and then we can use it. We want to have an expression in terms of R. Now, it is something that we are able to calculate. Right? If I define this theta over there, then indeed I can use the cosine law to express things in terms of R itself. So in this case, R, and I'm just going to express this as plus and minus, squared is R squared plus, in this case, this distance here, of course, is just D over 2. This is D over 2. So indeed, I get D over 2 squared minus plus R D cosine theta. Okay. So this is just the law of cosines, and I can simply write R plus, R minus in this way. Again, because I'm squaring, I'm not going to put an arrow on top just for convenience. Now, if I take R squared outside, then I can write this now as R squared 1 minus plus cosine theta over R plus squared 4R squared. Now, in this case, we are actually looking at 1 over R. And so let's take a look. What would be r plus minus, but in this case 1 over? Okay. And this would just be r 1 over r, 1 minus plus e over r cosine theta plus e squared over 4r squared to the minus half. Okay, so 1 over the square root of this. Now, in this case, what I can do is to now start making this approximation, because if I now look for a scenario where r is bigger, much bigger than d, then one thing that I can do is already get rid of the very last term over here, because d over r is small, and so d over r squared is even smaller. And given if r is sufficiently large, then this term can be approximated away, in which case I can simply write that this is just r to the power minus 1 minus plus over r cosine theta to the minus 1/2, which is again similar to r minus 1 plus minus e cosine theta over 2r, like this. Okay, so again, this is under the assumption that d over r is small. This is then how I can use this, and then the binomial approximation by bringing the minus 1/2 down. Now we are on our way. We have a way to express r plus and r minus in terms of just r. So indeed, let me repeat this. So if indeed r can be expressed, or 1 over r can be expressed as r to the minus 1 plus minus e cosine theta over 2r, this, then, well, what would be 1 over r plus minus 1 over r minus? Well, I can indeed do this now. So this 1 over r remains a factor over here. And then I get 1 plus d cosine theta over 2r minus 1 over r 1 minus d cosine theta over 2r, like this. Okay, the 1 over r drops out. The only thing that is left is, well, is what? Anyone? Cosine over r squared. Okay, let me at least put a wiggle here, just so that people realize that this is approximately equal to. So let's take a look. Okay, so this would be a dipole. And so something that we then typically call a monopole is when there's just a single charge. Okay? And then, this would be something that we would consider as a dipole. And so let's take a look at, you can probably already guess the trend. Right? Let's consider these multipoles. So if a single charge, right, let's call this a monopole, goes as 1 over r, and we've put something like this, and we call this a dipole, and that goes 1 over r squared. Phi. If this is minus and this is a plus, then it shouldn't, well, it shouldn't come as a surprise if I stack two dipoles on top of each other, but just with the opposite sign of a pattern like this. Well, what would I call this? I would call this a quadrupole. And well, what do you guess is the order in R? Xiaofeng is saying 4. Cyril is saying 1 over 4. Liu Ying is saying 3. Hong Hang is saying 3. We have a 50-50 split here. Anywhere between 3 or 4. Harry says 3. Okay. Can I get a show of hands who thinks it is 3? Okay. Raise your hand if you think it's 3. Okay, I can see 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 15, 16. We're getting towards more and more good stuff. Okay. I'd say it's about half. So far, only half of the people, maybe even less than half, 20 something, have said 3. Don't derive it, then 50%, 3, 50%, 4, 3.5. Okay. Okay, now just out of curiosity. Well, I mean, okay, someone writes it in Chinese. It's very useful. Computer analysis, very good. Okay, the answer is 1 over 3. Okay, so this is indeed, this 1, 2, 3. For reasons that we'll take a look at later, that will become apparent later. Okay, so actually, for those who are very curious, we could even do a so-called octupole, and then it should hopefully be completely clear. So this is a quadrupole, and I'm stacking another quadrupole. Oh, that's very poorly drawn. Okay, then I'm stacking another quadrupole like this, like fashion like this, and here. And this would be plus, this would be minus, this would be a plus, that would be a minus, and this would be a octupole. Not anymore. Octupole. And indeed, I hope people can guess this. This is r to the 4th. Okay, so you're starting to see this trend, right? So, what I can do is I can relate different kinds of fields to particular, uh, different patterns to different kind of orders in 1 over r. Right? So monopole is just single charge, that would be 1 over r. If I get something that looks like a dipole, I get a 1 over r squared, and then quadrupole, octupole, and so on. It goes on. And so this is something that hopefully you'll start to see, that this really is a series. Okay? And so we can take a look at this. And let me try to at least formalize this series to you in the following way. Okay, so let's reanalyze this, and let's do this properly now. So now let's do the proper multipole expansion. Because before we only looked at the like a dipole, and now let's look at the full multipole expansion. Okay. So again, we start off with a particular distribution, and let's put this is the origin, and let's consider a little bit of charge over here. So this arrow here is r prime, and let's take a look at some field over here. So let's call this r, and then we can now consider this to be r minus r prime. This is the observer. This is the charge distribution over here, okay, which is over r prime. And so the potential, how do we write the potential? The potential is simply given by AE, the integral rho as a function of r prime over r minus r prime v prime. And indeed, now what we want to do is we want to expand this 1 over, we want to expand r minus r prime to the minus 1. So we can do this using the following. Okay, so imagine that I've got r minus r prime squared. Okay. Using the rule of cosines, I can do r squared plus r prime squared minus 2r r prime cosine theta. Okay, but in this case, the quantities where there's no arrow, I just assume that to be the magnitude itself. Now this here, if I take r out, I can r squared, and here I get 1 plus r prime over r squared minus 2r over r, 2r prime over r cosine theta. Okay. So now we want to, in the case, we want to consider where r is much bigger than r prime. Actually, let me do that on a new page. So the multipole expansion. And so you're interested in the situation r is much bigger than r prime. So let's define the small parameter. Epsilon be r prime over r r prime over r minus 2 cosine theta. In such a way that indeed now 1 over r minus r prime simply 1 over r and 1 plus epsilon. Okay, so this is actually the expansion that we want to do. And so in this case, this here can be approximated by r to the minus 1 minus a half epsilon plus 3 over 8 epsilon squared minus 5 over 16 epsilon cubed, and so on. Okay, again, using a simple binomial approximation. Okay, now let's take a look, because we've defined epsilon to be this over here, this parameter over here, and so let's move things over a little to give a little space. So this is r to the minus 1. And if I now do this unpacking, I get 1/2 r prime over r prime over r minus 2 cosine theta plus 3 over 8 r prime over r squared r prime over r. Actually, let's create a little bit more space for myself. Okay, r prime over r minus 2 cosine theta squared dot dot dot. So now comes a slightly tricky part that requires a little bit more attention. So imagine now that I want to consider all the factors of what r prime over r. In this case, I need to start collecting the relevant terms. So here, I get one term. If I multiply this with this, I get one term that is first order in r prime over r. Okay, so that would be one single term. Now, how many terms are there in this case with r prime over r? Sorry, r prime over r squared. Anyone know? 2, okay. Which 2? Alex or Harry? Feel free to open your mic. You don't have to always type.
One contributed by the second term of the expansion, r prime divided by r times the one itself in the right bracket. And another one is from the factor r prime minus r to the square multiplied by 4 times cosine square.
Very good. So, okay, indeed, we see one from here, the first term, so and this term here with more or less this one squared. Right? If I expand this one here, I get 3 terms. And there'll be one term that has, that is 0th order to r prime over r. And since I have to multiply this by r squared, we get, again, another term. So indeed, if I look at this multiple expansion still, and in this case, we are indeed dealing with r minus r prime over, and this is just 1 over r. And indeed, I get 1 plus cosine r prime over r plus 3 over 2 cosine squared minus a half of r prime over r squared, and so on. Okay, in this case, the next term will be r prime over r cubed times some function g. Properly, plus dot dot dot. Okay. So you can indeed, you can start to see, this trend. Okay? And it shouldn't come as a surprise now that this is exactly the same. This is exactly the distribution, the multipole expansion that we considered here. Right? We see here, we see the monopole is 1 over r, dipole 1 over r squared. This is 1 over cubed, and this is 1 over r to the 4th. How do 16 poles look like? Well, that would be 2 octopoles. Okay, but typically I don't even know what a 16 pole thing is called. Let's see. That would be a hexadecapole. Hexapole. I don't know. Yeah, maybe that decahexa or hexadeca. Okay. Anyway, yes, that would be literally 2 octopoles together. And then you can stack you can stack 4 of these octopoles, and you can keep going like that. Okay? Now, obviously, you can see that the order in R goes down, right? And so we're dealing with things that are much less and less and less important. We're dealing with an expansion. And so what we end up seeing, right, and this is something that then we can take a break after this, is that we want to go towards 1 minus, we want to expand this, and I'll write this in a more or less systematic way as a series, r over r to the power n, and then some function, and I'm just going to label it with n. Okay, so these p's are all different functions, and I can already say that the argument goes cosine theta. So this is the expansion that we want to we want to do, want to be able to. And what we'll do after the break is is ask the question, what are these functions? What are these functions P of n? Okay, so this is a great moment to take a break. I think we can take 6 minutes now. So let's come back at 3:40, and we're going to indeed, after this break, we're going to take a look at what are these functions P of n. Okay, I'll see everyone in a minute. Okay, let's get back into it. Let's take a look. There are some questions. So Chin Pang is saying, what are these functions P of n? It says Legendre solutions, which yes, that is the correct. That is the correct thing. These are so-called Legendre polynomials, and so that's something that we're actually going to take a look at now. But before I get started again, let me quickly go through Jason's question. Okay, so Jason is asking whether I can say again how this multiple expansion tells us the dipole is 1 over r, quadrupole is 1 over r cubed. It doesn't yet. That's the thing. Okay, so at this moment, there's still no physical link between whether this is, the dipole is 1 over r. Now, of course, it is something that we've seen before, that the dipole is the thing that goes as 1 over r squared, right? And that's what we've shown here. Right? We started from here, that we go down and down, and then the first order for the dipole is 1 over r squared, right? The 1 over r drops out, doesn't exist. And so that's how we made the analogy to some dipole and some and this 1 over r squared. Okay. One thing that I'm not going to do explicitly, and that's something that you will have to either verify it yourself, is that all the others are indeed this 1 over r cubed and 1 over r to the 4th. That requires just a lot more algebra, right? So instead of 2 contributions here, I have to now add 4 contributions, and then I have to do all sorts of tricks with cosines and different angles and everything. But it does inspire us, right? So to have a picture of how how the expansion that I've done here in a mathematical way that ended up leading to this, how that can be interpreted in a physical sense. Okay. So that's where I'm kind of taking this, where I want to put this. But for the time being, indeed, okay. Oops. The solutions to these, okay, this is, if I fall for this again, then I am a donkey. Okay, these are indeed Legendre polynomials. Okay, just a show of hands. How many of you have or are taking 3051? Is it 51? Mathematical methods. Harry, do you mean last term, like the one that just passed, or the last term of this academic year, like next? Last year, term 2. Okay. So okay, let's see. Show of hands, who's taken 3051? Oh, that's a lot. Is that a compulsory course? Well, okay. I see still many people who haven't. Okay, so so when I say Legendre polynomial, at least some of you will know what I mean. Okay, so let's take a look. Okay, let's see if we can set out to prove that these Pn are indeed the Legendre polynomials. So for those who feel free to put your hands down, and let's take a first look at this. So okay. So Legendre polynomials. So does anyone know what equation generates these Legendre polynomials? Anyone know? And I'll give you a hint. It's a differential equation. Euler equation. Okay, I don't know what Euler equation is, to be very honest. Wait, no, Euler equation, that can't be right. Yeah, I'm also very bad with. Okay, so but Euler's equation is this one. No? That's this one. Anyway, I'm exceedingly bad with names as well. Okay, so Tom is saying the following. Let's see if I can agree with this. He says, so I'm just going to call this Legendre's equation. I don't actually know exactly whether this is the right name, but it doesn't matter. I'll put it down here. So it's a differential equation, and it should be 1 minus x squared y prime prime minus 2xy prime plus, and I can use n here, n minus 1 y equals to 0. Okay, so indeed Tom's solution is correct. He writes lambda there. You can show that you can actually force this lambda to be n times n minus 1. Okay? But that's detail. So the Legendre's equation, then this equation has a particular series solution. There's many different solutions that you can write, and these what we call Legendre polynomials. So the solutions are the so-called Legendre. Okay, now this is not the exact moment where I want to discuss in more detail these Legendre polynomials, but one thing that I can say is that, of course, there are infinite many, and they're labeled by n, where n is an integer, and they're actually polynomials. I'll show in the end. I'll show some examples of these Legendre polynomials. But what is important to take away is indeed this this form here. Okay, so if I can show that, in this case y, or if I go back, if I can show that these Pn satisfy, right, this Pn over here satisfies this differential equation, then it's something that this guy called Legendre has already solved, and we know all the solutions to these. So instead of needing to do this explicit expansion all the time, we can use maybe smarter tricks to do it. And in order to do so, let's consider a particular concept that I want to, and that is so-called generating function. So one thing that I can do is I can consider a so-called generating function. Now, what is a generating function? A generating function is simply one that I can write in this form. G is a function of x and some label h. Okay. Well, let's make this n. It's easier to follow n in such a way that n 0 to infinity fn of x and oops, oh, that's bad. Okay, was h to the power n. So I'm writing here on the left hand side is a function g, and which depends on x and some dummy expansion variable h. And then on the right hand side, I see this as a series where f are functions labeled by n and h to the power n. And these f of n's are then coefficients that go in front of h to the power n. And indeed, under certain circumstances, it is possible to find g in a closed form. So let me show you what I mean by this. So consider the functions p of n in such a way that I can write the following. Write that 1 minus 2x h plus h squared to the power minus a half equals to the sum n from 0 to infinity n of x h. Okay, so this is an example where this generating function g I can write in a closed form. And I can show that the left-hand side is then equal to the thing on the right-hand side. Now this is a particular form. Okay? So I'm not saying that every function g is like this, but here I'm writing a particular form. Okay. Now this form is something that you should hopefully recognize, because if I go back to the expansion that I've done, for example, let's see, what would be a better thing to do? Right, something like this here. So if I look at this factor over here, then this is indeed of the form 1 minus 2xh plus h squared. Okay? And in particular, what I see here is that then this indeed becomes 1 minus 2xh plus h squared to the power minus a half. So this is indeed what we're looking for. This is the form that we're looking for. And so let's see if we can prove. Okay, and this part is going to be a little bit algebraic, but that's fine, right? It's something that we ought to be able we ought to be comfortable with. Is that we want to show that this generating function is associated with a series in terms of the Legendre polynomials, in such a way that I want to prove that Pn indeed satisfies Legendre's equation. Okay, so this ordinary differential equation in this case. So let's see if we can we can do this. Okay, so let's start by genre. And let's start with our starting point, and that is this following equation, our generating function, g of h equals 1 minus 2xh plus h squared to the power 1 over 2 equals to the infinite sum from 0 to infinity of Pn as a function of x, h to the power n. That's our starting point. Okay, now let's do the first step. First step is, let's say we differentiate both sides with respect to x. Okay, so again, actually, when I'm doing this, hopefully, I'll try to go quite slow, but grab a pen and pencil, pen, whatever you like to use, and write along. Write along. See if you can follow. Okay, so the first thing is I'm getting this generating function, and I am going to differentiate with respect to x and h. So first, with respect to x, what do I get? On the left-hand side, I simply get h times 1 minus 2x plus h squared to the power minus 3 over 2. Okay, so that's on the left-hand side. And on the right-hand side, what do I get? Well, I get that this is simply the sum, and I'm going to stop writing n equals 0 all the way to infinity, and I'm just going to call this Pn prime x. I'm even going to remove this as a function of x. We all now know it is a function of x, and it's still h to the power n. Where in this case, p prime is simply dp over dx. Okay, and double prime is then, of course, two derivatives. Okay, now what about with respect to h? Give you a quick minute to see if you can follow. So let's differentiate this expression here at the top with respect to h. Did I miss an h inside the bracket? Yes, you're right. Thank you, Jason. Okay, so now let's differentiate this equation at the top with respect to h, and it should be x minus h, 1 minus 2xh plus h squared to the power 3 over 2. And the right-hand side, because now we got h to the power n, so we differentiate h to the power n, we get something that goes as the sum n pn h n minus 1. Okay. So now we can start pulling things together. And in particular, we can actually take a look at this top equation over here, so this generating equation, and this equation over here. Let's see if I can put these two things together. And so what I'm going to start off with is the following. So I'm going to this here. It's easy to follow. So indeed, I'm going to multiply this equation over here, both sides with 1 minus 2xh plus h squared. So I'm getting the following: 1 minus 2xh plus h squared. And this is simply Pn prime Hn. Okay, so I'm starting off with this equation over here, but I'm going to multiply both sides with 1 minus 2x h plus h squared. And so on the right hand side, what do I get? I get h 1 minus 2x h plus h squared to the power minus a half. Okay, so now I use the top equation, this equation over here, to substitute for 1 minus 2x h plus h squared to the power minus a half. And so I can get the following expression. This is just h, the sum, n, hn. Okay, hopefully everyone can follow these steps. So I've simply used this expression over here, the one in the middle, and the one on the top. Okay, so now here comes actually something important, because one thing that I can do here is keep track of all the powers in H. Okay, so what does that mean? Okay, so in this case, if I put H inside here, I get, Hn plus 1. And this term over here, it remains Hn. This term over here is Hn plus 1. This term over here is Hn plus 2. Okay? And so ultimately, the left hand and the right hand side should be the same. So every order, the coefficients with the same power of n should be equal to each other. So I can turn this equation into something that, where I'm actually going to equate in the powers of n plus 1. Okay? In other words, this is easier to understand in this way. I'm going to make n plus 1. I'm going to relabel it to n. Right? It doesn't matter. These are still just integers, and I'm just going to shift all the equation by subtracting 1. So this term over here becomes n minus 1. This term here becomes n, and this is n minus 1. And so I can turn this equation into the following equation, right? Just by equating all the powers in n, I can now turn this into Pn equals to P prime n plus 1 minus 2x Pn prime plus Pn minus 1 prime. Okay. So again, this is an important step, because here what we're doing is we're collecting all the coefficients that are associated with h to the power n. But I've done a little bit of a sidestep where I'm actually relabeling n plus 1 to be n. Right? So here, I'm just relabeling everything, or collecting everything in p to the n plus 1, which I relabel as p to the n, pn, sorry. And so the coefficients are simply these ones that then follow along. I've got one that is plus 2 from this one. Okay. I've got one that is just plus 1. I've got one that is plus 0, and this is also plus 1. And so I'm getting this so-called recurrence relationship. So that's the first step. Now, I can actually do this again, but instead of looking at the top equation, combining with the middle equation over here, I can actually combine these two equations over here to get another recurrence relationship out. So that is what we're going to do next. And so I'm going to equate now these two equations in the appropriate way. So let's start off with writing the following. I'm going to write H sum of n H minus 1, sorry, n minus 1 equals to H x minus H, and here I'm getting 1 minus 2xh plus h squared minus 3 over 2. Okay, so let's take a look here. So what have I done? So here I'm simply going to, again, multiply this equation here by h. I'm putting h here, and I'm putting an h here. Okay, so this is putting an h here, and then here is an h here. And this equation. Okay, so hopefully everyone can follow. So now we're combining these two equations over here. Now, of course, we've seen before that we can substitute this in here, this minus 3 to 2. We can substitute this using this first equation that I've written over here. And so this then effectively becomes x minus h sum of Pn prime h to the power n. Okay, so that's just simply this one. So this h, 1 minus 2xh plus h squared minus 3 over 2 is indeed this term over here. And again, I can now come up with another recurrence relationship by now equating again in the same powers. Properly, h n minus 1, and I can now again I can put this h inside here, and this is just h to the power n, and I can do the same with here piecewise in such a way that I can again start collecting all the powers in n. Let's do that here, and I get a second recurrence relationship. Second recurrence relationship that goes as n Pn equals x Pn prime minus Pn minus 1. Correctly. A prime here. Let's see. That should. Let's see. This one h x minus plus 1. This is plus 1. Yeah, I think this should be okay. Anyway, I'll fix this in the if there's a typo, then I'll fix it. Okay, so now we can eliminate this. No, it should be minus 1. Okay. So now we can eliminate this. Yeah. Okay. Yeah. That should. Okay. Yeah. This is a little bit, a lot of algebra. But now I can use relationship that I found before, I can use this equation over here to get rid of additional terms. So I can now combine this equation. Combine this equation with this equation in such a way that I can now write this. So using first recurrence relationship, I can now write that I get n plus 1 pn plus 1 prime minus x p n. Okay, so simply if I add this equation to this side over here, well, okay, let's try this a little bit easier. Okay, so let's write this equation. Let's copy this equation down. So I'm getting Pn plus 1 prime minus 2x Pn plus Pn minus 1 prime, primes, and I am putting this Pn, I'm putting this equation down as well, equals x Pn prime minus Pn plus minus 1 here, minus 1 here. So if I add these two equations up, I am getting the thing that I desire. I'm actually getting this over here. I am getting n plus 1 Pn equals 2 Pn plus 1 prime minus x Pn prime. Okay. Now again, I can interchange this by relabeling things again. And I do apologize, this is a little bit more algebra, but we're getting very close. So we can relabel this now from n to n minus 1 in such a way we just subtract 1. So we just write this as P n minus 1 equals to P n prime minus x P n minus 1 prime. Okay, so in this case, what we've done is we've gone n to n minus 1. Now, again, when we look at the second recurrence relationship here, I can also write this. If I just multiply both sides by x, I get xn Pn equals x squared Pn prime minus xp minus 1 prime, like this. And if I now add this equation onto this equation over here, sorry, if I now subtract this equation from this equation, I'm actually getting the following. Let me copy everything down. Okay, so what do I do? I get that this is n p n 1 plus n prime minus x p n prime, and the other one that I had was x times this, so I get x n p n. This is x squared Pn prime minus x Pn minus 1. And now I'm subtracting this from each other just to eliminate that one. Should be n minus 1, right? Thank you very much for spotting that one. Correct. Okay, so if I subtract these two from each other, what do I get? Indeed, I get n. Oops. This is n Pn minus 1 minus xn Pn equals to Pn prime minus xPn minus 1 prime minus x squared n prime minus xPn minus 1 prime, like this. Okay, now this is simple reorganization. I get n, this is Pn minus 1 minus xPn equals to 1 minus x squared Pn prime. Right? These two terms, oops, this should be plus. Okay, so these two terms, the second one and the fourth one cancel, and I get this one left. Okay, we're almost there. So now differentiate this one, okay, with respect to x. Okay, so what do I get? I get 1 minus x squared p double prime n, right? That's this side here, minus 2x pn prime equals to n minus 1 prime minus x pn prime, and all of this minus pn. Now, this term here is actually one of the recurrence relationships that we had before, which is given over here. Yes. Well, okay. It can also be seen here. Second recurrence relationship here. And that is simply this term over here. And so I can indeed put this in now in such a way that I get the following. I get this now equals to, let me make sure I get this right. So this is n, and this is minus n pn, and all of this is minus pn. In this case, this is indeed n minus 1. Whew. Okay, so indeed, we have worked it out in such a way that now, I indeed get 1 minus x squared and double prime minus 2x pn prime my plus n plus 1 pn equals to 0. Very proud. Okay, so this is indeed what I set out to prove. Okay, I do apologize. There's a lot of maths to it, but this actually helps because instead of going through this big expansion and then collecting all these terms that I need, I can actually just simply notice that I'm actually having a generating function, right? I can have that I have a generating function of this form here, that now I know that this closed form, okay, which is associated with doing this expansion here in this form, right? This is a form 1 minus 2x h plus, that I now know I can write this of this form here, and that these PNs are indeed the Legendre polynomials. And then now it's simple. I just look them up in a book. right? These Legendre polynomials are all being calculated. One thing I can safely say is that we are actually going to take a look at these Legendre polynomials later on when we're considering the Poisson equation, or actually, the Laplace equation in spherical coordinates. That's actually where they will come back, and they will help us getting a solution out. Okay, so this is actually a good point to stop. And next week, what we'll be doing is we'll actually take a look at what the significance is of being able to write this generating function and showing that these are Legendre polynomials in such a way that I'm able to calculate different components. Right? I can calculate the monopole contribution. I can calculate the dipole contribution. I can calculate the quadrupole contribution. And so these are ways to get solutions. Here, these are ways to get solutions for when I'm far away from the source. So when I'm far away, I typically only need to take the first non-zero order, or maybe the first two non-zero orders, in order to do that, in order to calculate or to approximate it in a good enough way. And so, now that I know how to expand this 1 over, now I know how to expand. Oh, I can't find it back in. This is fine. Now I know how to expand this over here. I'm able to now look at the first few orders to see what are the strongest few contributions to this field, and that actually gives me an excellent solution to the potential, or I could even use it as in the vector potential as well. Okay, let's stop here, and next lecture we're going to take a look at how to use this in order to solve some problems. Okay. Anyway, let me ask if there are any questions at this moment. I don't see any hands up or any questions. Oh, I see still 2 hands up, but those are actually questions. Pearl, do you mind writing this in the full chat, so I know how to answer? Let's see. So Pearl is asking whether. Oh, let's see. If I need a little boo boo. So that should be a plus, right? Is that what you're asking? Yes, that should be plus. How? Last statement. Yes. Because I'm taking this minus sign and this minus sign outside the bracket. Okay, any other questions? If not, let me turn off the recording.